line. So least squares regression line. It is a very specific type of regression line, and we'll talk about how it's made. The good news, guys, is that your calculator is going to make it for you. Okay, we do just need to know, like, why is it called the least squares regression line, and so that's what we're going to start with. So a good regression line makes the residuals as small as possible. Obviously, the residuals are the distance between the actual value and the prediction. And so if our line is close to the actual values, then that means it's going to make really good predictions. So we want really small residuals. We want our predicted values as close to the actual values as possible. So we use the least squares regression line. It is also referred to as the LSRL. The LSRL. So the least squares regression line is the line that makes the sum of the squared residuals as small as possible. Okay? And we'll talk about how your calculator is going to do it for you. We'll talk about the process, but again, I don't want you guys to get too hung up on the process because the calculator will do it for you. Okay? But that's why it's called the least squares regression line. So I'm going to show you how it works. Did y'all get all that? Yeah, cool. Yeah, cool. All right, so here's a scatter plot of that Ford F-150 data that we were talking about on Monday. And this is the number of miles driven and the price, okay? So the residuals are these vertical lines. So the residual is the distance between the actual value and the prediction line. So, like, some of these have really big residuals, okay? So some of our data values are really far from our prediction line. Some of them are really close. That's the little bitty residuals. All of the data values on the top would have positive residuals. The data values on the bottom would have negative residuals. If I were to add all of these numbers up, all of these residuals, some of them positive, some of them big, some of them small, some of them negative, some of them big, some of them small, I would actually get about 0 every time because they're kind of canceling each other out. Some of them are big, some of them are small, some of them are positive, some of them are negative. So in order to take that away, what happens is we square the residuals. What is -2 squared? Positive 4, right? What is -6 squared?
36.
Positive 36. Anytime I square a negative number, it makes it positive. So what we do is we square the residuals, literally and mathematically, okay? So we take this residual and we turn it into a square. So we have little squares and big squares. Whenever I do that, I'm basically finding an area, okay? So if I take this residual, for example, and I square it, I'm basically finding the area of that square. And if I take this residual and I square it, I'm basically finding the area of that square. And then I take this residual and I square it, I'm basically finding the area of that square. And what we do, our calculator does, is it adds up all those areas, which now will not cancel each other out because I've taken out the negatives by squaring all of these residuals. And so these squares, I add them all up, and my goal is to make the sum of those squares, of those residuals, the least possible number that I can. And your calculator does this, and it does it really fast. So it'll kind of look at the values, and it'll tip the line back and forth, move it up and down, and it'll find the smallest possible sum of those squares of all of those different areas. And that's how we come up with the thing called the least squares regression line. It's the least of the sum of the squares of the regression line. Make sense? Ish? Again, you guys never have to do this process, which is so nice. Okay, you never have to add up all the areas or square the residuals yourself. The calculator is going to do it for you. But that's why it's called what it's called. Least squares regression line. All right, so That's all of the reasoning behind what it's called. Now, how do we actually do it? Okay, so how do we actually get this least squares regression line? So what we do is we have to plug our data into our calculator. Do you guys remember how to plug data into your calculator? Stat, edit. Okay, stat, edit. That's going to get you to where you can plug data into your L1 and your L2. L1 is where you're going to put your explanatory variable, the x-axis variables. L2 is where you're going to put your response variable. Okay, so you go to stat, and then you hit enter on edit, and it will bring up this L1 and L2 list. Okay, so what I want you guys to do, I know this is going to take a minute because these are really big numbers, but I want you guys to enter these numbers into your stat edit list. All right, now there are 3 rows here, or 3 sets of data. You're going to put the miles driven in the X or the L1 column. So L1 goes miles driven, and you can just put them in one big list. So once you get to the end of this line, go to the next line, and then the next line. And then you'll put the price into L2. I know this will take you just a second, but go ahead and plug all of that data in under stat and edit. So we have our data input into our L1 and L2 list. And so here's what we're going to do now. All right. Next thing what we're going to do is we're going to go to stat. Hit the right arrow over to where it says calc. And we are choosing number 8, which says ln reg a plus bx. I'm fairly certain in Algebra 1 and 2, you chose number 4, which says linear regression ax plus b. That's because in Algebra and Algebra 2, you use mx plus b. We use a plus bx, okay? So what the difference is that this is going to switch your a and your b, okay? And put it in the way that we do it, with a as the y-intercept and b as the slope. If you use number 4 like you did in algebra, your a is going to be your slope, and your b is going to be your y-intercept, which is backwards for us. Okay, so make sure you guys are using number 8. And then you will probably see this. You want to make sure your x list is L1, your y list is L2. You can leave your frequency blank and your store regression equation blank, and you could go down to calculate and then hit enter. For those of you who have a little bit of an older calculator, you are probably just seeing ln reg a plus bx on your calculator screen. So you're going to want to put an L1. To do that, you're going to hit second and the number 1. Then you're going to put a comma, which is the button right above the 7. And then you're going to want to put an L2, which is second and the number 2. Okay, so if you have an older calculator that's not showing this, you're going to want to make sure you have an L1, comma, L2. Okay, and then everybody can hit calculate. Okay, so everybody hits calculate. All right, so once we hit calculate, we should see, now most of you are probably only seeing this top part, which says, which is right here. You're probably only seeing the A and the B. You're not seeing the R squared and the R. That's okay. I'm going to show you how to get those to show up here in just a second. But the A is your y-intercept. The B is the slope. If your numbers are slightly off, that just means you had a little bit of a typo. Don't worry, but this should be pretty close to what your numbers are, okay? Is everybody seeing the A and the B? Okay. All right, so R and R squared. R is the correlation, which we've already talked about. It's the strength and the direction of our scatter plot. And so what we're going to do is I'm going to show you guys how to get those to come up. You're going to want to go to Stat Diagnostics. Okay, so to do that, you're going to hit the mode button on your calculator. It's near the second button. You hit mode, and you're going to scroll down until you see the stat wizard and the stat diagnostics. Make sure both of them are turned on. Okay, stat wizard and stat diagnostics under mode, and you're going to want to make sure those are turned on. If you have a calculator that you are not seeing Stat Wizard and Stat Diagnostics, then what you have to do is go to the catalog. You would go to second and 0 for catalog, and you would scroll down until you see this phrase, diagnostics on, and you would hit enter and then enter to turn it on. Okay? Has everybody got their Stat Diagnostics on? And the wizard is on and ready? Okay. So now we're going to repeat this right here. Everybody's going to go to Stat, Calc, number 8. Again, make sure you've got your L1 and L2. If you've got the older calculator, you're going to make sure you put in second and the number 1, comma, second and the number 2. And now when you see your screen, you should see R squared and R. All right? Is everybody seeing R and R squared now? Perfect. Do you guys remember if R is a negative 0.815, what does that mean about this correlation? So strength and direction. If it's negative 0.815, what does that mean about the correlation between these two variables? It's negative, perfect. And is it strong, weak, or moderate? That would probably be strong, okay? Anything around 0.75 or higher is usually considered strong. So this would be a strong negative association between price and miles driven, okay? What questions do you guys have about that? Feeling good so far? Okay. Now we're going to see, do you guys remember how to do a scatter plot? Okay, scatter plot. You're going to go to second and y equals. That's your stat plot. Make sure you turn it on. Make sure you hit enter on. Make sure your scatter plot is selected. Your x-list is L1, y-list is L2. And now your scatter plot is on, okay? If you hit graph, zoom 9, you should see your scatter plot, okay? Now what we're going to do, everybody see your scatter plot?
Wait, what do you hit after second y equals?
Second y equals, make sure your plot is turned on. So make sure it's on.
All of them stay off.
Okay, so hit enter on the plot 1. Hit enter on plot 1, and then hit enter on. And then make sure you've got that first scatter plot, or the first graph is selected. Okay, now everybody hit graph, top right, hit graph, and then zoom number 9. You should see the scatter plot, but you probably don't see the line right now, okay? So we're going to get the line to show up by going to just regular y equals. Where are you at? Do you see the scatter plot, Austin?
Yeah.
Okay, perfect. So we want to get the line to show up. So we're going to go to regular old y equals. So hit y equals. Got it? Cool. Now we're going to put in the equation of the line that we got when we went to the linear regression. And so under y1, you're going to put in that equation. 38,257 minus 0.1629x.
How do we get that equation?
So that was when we went to, let me go back. When we were on this screen right here, it told us the A and the B. And so the A is our y-intercept. And so we would literally just write this on our paper.
Oh, right. Okay.
Yeah, we would just write it on our paper. And then we would go to the y equals and type it in ourselves. Yep.
Where do we get x from? Like, how can we get that one?
X is the button is to the right of the alpha button. It says like X, T, theta, something else. I don't know. Okay. And so we're putting in that equation. 38,257 minus 0.1629x. Once you do that, hit graph again. And now you should see the scatter plot with the line. Okay? Does everybody see the scatter plot with the line now? Cool? Awesome. All right, so this page right here is going to be very helpful for making sure that you know all the steps. Okay, all the steps are right here for you. Okay, and so that's how you do the scatter plot with the least squares regression line. Again, your calculator, the moment we hit enter on calculate, it figured out what the best line was by finding all the small sums of all those squares. So your calculator did a whole lot of work really fast. Okay? Yes?
Once we got the equation, what do we click after that?
Now that's where you go to y equals, just regular old y equals, and you would type it in.
Yeah,
okay?
I know, but like, how do we get the line?
Oh, okay. Then you hit graph. And then if you, it should draw it there for you. Cool?
Yeah.
Now, you don't have to look at the scatter plot first. You can just turn the scatter plot on, then go to y equals, put the line, and then do zoom 9, and it will do it both at the same time. Okay? Any other questions? Cool. Okay. Here's what I'm going to recommend because we're going to do an example. This one does not have as much data, so that's a good thing. I highly recommend that you clear your calculator. Do you guys all know how to clear your calculator?
No.
Second plus 712. Second plus 712. What that just did is it cleared out your y equals. It cleared out your scatter plot. It cleared out your y equals. It cleared out your list. It cleared everything out so you have a fresh start. By the way, anytime you guys get an error, usually that's the fastest way to start fresh. Just second plus 712. All right, so we're going to do this example. The following table shows the foot length in centimeters and the height in centimeters for a random sample of 6 high school seniors. Use your calculator to calculate the equation of the least squares regression line for predicting height from foot length. Okay, so we are going to put our foot lengths in L1. Again, once you get to the bottom of this list, just continue with the second side. And then we're going to put our heights into L2. We're going to put that data in. Okay. Got your data in? All right, once your data is in, you're going to hit Stat, hit the right arrow over to Calc, and you want number 8, the one that says Lin Reg A plus BX. Okay, and then it should give you, for those of you who don't have the updated calculators, you need to make sure you put that L1 and L2. For those of you who do, you just go down to calculate. All right, and then it should tell you what A equals, and it should tell you what B equals. So what does it tell you that A is? 82?
Yeah.
All right, and what does it tell you that B is? 3.3?
Yeah.
We'll just go with 3.3. All right, cool. So how do I use that to write the equation of the line? So y hat, do you guys remember what the hat stands for? The hat stands for the fact that this is a prediction, not an actual y value. So these are going to be predicted values, not actual y values. So y hat equals A, so that would be 82, plus, because it was positive, 3.3x. Okay. And then we can make a note that y is height and x is foot length. And now we have the equation of our least squares regression line. And then I could do things like calculating the prediction if somebody has a foot length of 32. And so I would plug in 32 here, find their predicted height, and then I could find their residual by taking their actual height and subtracting their predicted height. And so now I can do all of the calculations that I would maybe need to do for this particular example. Cool? Questions, comments, concerns, thoughts, feelings? Do you want to look at the graph again? Let's do it. Let's do it. So let's all go to y equals. Everybody go to y equals. And go ahead and plug in your equation. 82 plus 3.3x. So we're plugging in our equation to y equals 82 plus 3.3x. We don't need them at the moment, but I'll remind you how to turn that on after we do our scatter plot. Okay, so we've got our y equals 82 plus 3.3x. Do you guys remember how to turn on your scatter plot? Second y equals, hit enter on plot 1, hit enter on. Now your scatter plot's turned on. And now how do you see the graph? You hit graph. And if you don't see anything, zoom 9. Zoom 9. Now you should see the scatter plot with the line as long as you type the line into y equals. How we doing? Does everybody see it? Perfect. Okay. Do you guys remember where to go to turn on the R and R squared? The stat diagnostics, which is under mode. So everybody hit mode. Scroll down. Unfortunately, like this really stinks. I don't know why TI does this. Unfortunately, when you clear the calculator, it does turn this off every time, which is silly. If you never clear your calculator, it will never go away. But anyway, so mode, scroll down to diagnostics on, stat diagnostics, turn them on, make sure your stat wizard's on, everybody's on. And then we go back to stat, calc, 8. Now you should see R and R squared. The closer the dots are to the line, when you looked at your scatter plot, the closer the dots are to the line, the stronger your R will be. And then tomorrow we'll talk about R squared and what that means. Cool? Cool. All right, we're going to talk really quickly about outliers and how they affect our least squares regression line. All right, so we're going to talk really fast about outliers. All right, so here's a scatter plot that has 10 points on it, and it's got a correlation of 0.4004, so it's not that strong. It's fairly weak, but we do have a least squares regression line showing. Okay, you will notice that the least squares regression line goes through the point x bar, y bar, which is the mean of x and the mean of y. That's where these vertical and horizontal lines are coming together. That point right there is x bar, y bar, the average of x and the average of y. That point is like the tipping point for our regression line. And depending on what I do now will change my line and will change my correlation, okay? So the first thing we do is we add a point that is We add a point that is far on the right side, but it's right on the line, okay? So notice what happens to the line itself. What happened to the line from the original to the new? Anything happen to it? Did it change its slope? Not really. So really, it kind of didn't change, but what happened to the correlation coefficient? It got stronger. Why is that? Yeah, so that dot makes my correlation stronger because now the data's not just good right here. Now the data's good all the way out to here. So we've got a really good line that works all the way out there. Okay? So our R got stronger. Okay? So R got stronger. But the slope and y-intercept did not change. So that basically shows you that if you add an outlier that is on the trend of the line, it's not going to change your line itself. It'll just make your correlation even better. It's like, all right, this line works even way out there. Cool. So we've got a stronger situation going on here. Okay. All right, let's change to another point. So what if we add a point that is on the far right, but it's high above the original line? What do you guys notice about the line? Yeah, so the line got steeper, okay? So the slope changed. And then pretend that like this is your y-intercept right here. Let's pretend that's where our y-axis is right here. Like this is your x and your y. Would the y-intercept change from here to there? A little bit, okay? So yeah, my y-intercept, because this new point is pulling the line up, it makes the y-intercept go down here, okay? So it kind of tilts the line. So this outlier, which is far away and above the least squares regression line, it's going to cause our slope to increase. So the slope increases. Slope increases. The y-intercept decreased and went down. And then what happened to the correlation? Also got stronger, okay? And R got stronger. Okay, those are the things that happened for this particular point, okay? Now, there's lots of different places you could put the dot, so we'll see some more here, and you'll see that depending on where the dot goes, changes things in different ways. So the next one, we put a dot on the far right, but now we put the dot far below the original line. So what happens to the slope? It decreases. What happened to the y-intercept? So it stayed the same?
It looks like it. It's at 0, 0.
So remember, we're looking at the y-intercept as like right where this is. We're thinking that this is x and y like this. Okay, so our y-intercept would be like right here. And if I look at where that goes over here, it did go up a little bit. Okay, so when my line got less flat, when the slope decreased, this y-intercept increased. It went up, not a ton, but it did go up some, okay? What happened to the correlation? It got weaker, but look, it didn't just get weaker. It turned negative. Like that one dot changed my correlation from a positive correlation to a negative correlation. And so one dot can make a huge difference. That's the biggest idea here, is that one dot can make a really big difference. So for this one, my slope decreases. My y-intercept increases just a little bit, not a ton, but it does increase. And my R got weaker and turned negative.
How do we know what the y-intercept is?
So we're thinking about, think about a graph, right? So we're thinking that this line on the far left is our y-axis, and then the bottom here is our x-axis. So that's what we're looking at for our y-intercept. That's what we're considering our y-intercept. Yep, where the line starts on this graph. Yep. Yep. This x right here, or this coordinate, this is not necessarily the coordinates. Or this is just your x, your mean of your x values and your mean of your y values. This is not the coordinate. We're thinking of this as the coordinate.
Okay.
Otherwise, yes, I would agree that would seem like it doesn't change. All right, let's look at another example. Now, we're adding a point that is far above the least squares regression line, but it's near this average x line, okay? So it's near the average x line. What happens to the slope of the line? It did increase a little bit, okay? It did increase a little bit. What about the y-intercept? So again, we're looking at this point right here. It did also go up just a little bit, okay, slightly. Went up just a little bit. Notice, though, that your average y value here, notice that line did go up as well, okay? Because now I have to take into consideration that value that's way up here. What happened to our correlation? It got weaker, okay? All right, so our slope and y-intercept increased a little, not a ton. In fact, even if some of you said, I didn't really change it that much, I probably would say, yeah, you're probably right. But our slope and y-intercept increased a little bit, but we definitely got a weaker correlation. A weaker correlation. Okay? All right, here's another one. If we add a point that is below, so this one's way down here, what happens to the least squares regression line? What happens to the slope? It's about the same, right? That's the tip of the line. And then the y-intercept, maybe it goes down slightly, but not a ton. Also, I will say this dot's not that far away from the data, so it's not going to change your line very much. And what happened to our correlation? It got weaker, okay? Got a little bit weaker. So again, depending on where your dot goes, it changes some things, okay? But in general, here's some kind of generalized rules, okay? Here's a summary. When outliers are far away from the data in the y direction, so from side to side, like the first few that we looked at, but they are in line with the least squares regression line, the equation of the line is not affected much, okay? My slope and my y-intercept stayed pretty close to the same. But the correlation coefficient gets stronger the closer that data point is to the line. Okay, so if I add a value that is on the line but far away, my line doesn't change much, but my correlation coefficient is stronger. When outliers are far away from the data in the y direction, but not in line, so they were either far above or below, then the slope and the y-intercept will both be affected. They might change in different ways. It depends on where the dot is. And the correlation will change depending on where it is. Okay, so we saw one example where the correlation got stronger, one example where the correlation got weaker. Just kind of depends. And then when outliers are far above or below the data in the x direction, this is just going to shift our line up or down. The slope is not really affected that much. However, the y-intercept will increase if the outlier is above. It'll decrease if it's below, and the correlation gets weaker. I promise you guys it gets way easier as you just kind of look at it and see how it kind of changes things once you see some examples. So let's look at a quick example real quick. So on this example, the question is, does the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of young children recorded at the age in months at which each of the 23 children spoke his or her first word, and the child's Gesell adaptive score, the result of an adaptive test taken much later. This is a scatter plot that shows the relationship between the Gesell score and the age at the first word, along with the least squares regression line. We have two outliers, child 18 and 19. They are identified on the scatter plot. All right, what effect does child 18 have on the equation of the least squares regression line and on the correlation coefficient? And then what effect does child 19 have? So let me show you guys a couple of cool things here. So the actual solution for part A about child 18. So because the point for this child is below the line on the right, so think about if I were to do like average X and average Y. So because that's kind of like my tipping point, like my seesaw point, okay? That would be where my X bar, Y bar would be, my average X and my average Y. So because that value is far to the right, you think about it as like it kind of weighs down the line. So that child's kind of pulling down on that line. So what that does is it makes the slope steeper, meaning more negative. Okay, so the slope is going to be steeper because that child's pulling down on that line, if you kind of think of it that way. That means if I'm pulling down on the line right there, and if this is a seesaw, that means this side of the line's going up. That means that the y-intercept would be going up because of that child. Does that make sense? Okay, so that child increases the y-intercept. The slope is steeper, the increase in the y-intercept, and then this correlation would be, this child would make the correlation stronger because they're pretty close to the line and they're far away from the rest of the data, so it kind of makes it like the line looks even a little bit better. It makes the line a little bit more valid even far away. So if I'm going to show you guys this is kind of cool. With all 19 children, so including this kid, 18, there's my R. My R is negative 0.64. If I take that child out, my R goes to negative 0.33, closer to 0, meaning weaker, okay? And you'll notice that the line gets less steep and the y-intercept goes down. So that child is causing the line to be more steep and the y-intercept to go up, okay? So that's kind of a cool little visual of what's going on there. What about child 19? So again, if I think about where my X and Y averages are, and this is my seesaw point, this is where my X bar, Y bar is, my average X and average Y. This child is probably going to take that line and just pull it up because it's right there in the middle there, close to the middle. So this is going to pull that whole line up. So probably the slope doesn't change much, but the y-intercept has been increased because of that child. The correlation, however, would be weaker because this child's outside of the scatter of the data. So here's the kind of that visual on this one. So this child, it says that it is, so see this, without that child, the correlation got stronger. So with the child, the correlation got weaker. Okay, so with the child, the correlation is negative 0.64. If I take the child out, it gets stronger because I am removing that kid. Make sense? And again, look at the difference in the line. The line just kind of moves, but not a ton. It just moves up a little bit. So there's not a ton of effect on the regression line. Cool? All right. Let's look at the yogurt problem real quick. So here are the data on the amount of protein and number of calories in a random sample of 10 brands of flavored yogurt. A scatter plot with the least squares regression line is also shown. And so it says to calculate the equation of the least squares regression line using technology. So what we're going to do is we're going to plug in the protein, because that's on the X. We're going to plug that into L1. And you're going to put both of those lines into L1, protein. And then your L2 is going to be your calories. So if you guys want to, those of you that are following along, if you want to plug that in, and then we'll get the equation of the least squares regression line. Okay, you guys, remind me because I'm old and I forget things. Once I have my data in my stat edit, what do I push to get the line? Stat, calc,
and then go 9.
8. Stat calc 8 for linear regression A plus BX.
No, that's for the
Stat calc 8. And then if you have the updated system, just keep hitting enter till you get to calculate. If you don't, make sure you put an L1 and an L2. And what did you guys get for your line? You should have gotten this. You may or may not have R and R squared. That has to do with whether or not your stat diagnostics and all that fun stuff is turned on. But hopefully you got an A of 228.41 and a B of negative 8.25. Did y'all get that? Perfect. So there's our equation. Y is the number of calories. X is the protein. If you want to see the R and R squared, that would be where you go to mode and turn on your stat diagnostics. You would go to mode, go down to turn on your stat diagnostics, and then there's your R and R squared. All right, and then let's look at part 2, number 2, I mean. We have that outlier. That outlier is Joe's Greek yogurt. Let me go back to the scatter plot. So here's Trader Joe. There's his yogurt. What's going on with Trader Joe? It says, what effect does this point have on the equation of the least squares regression line? So is that point, what's it doing to the line itself? So think about that point, if I took it away, what would happen to the line? What do you think would happen if I just took that point away? Would the line go up? Nope. The line would go down. If I took that point away, the line would go down. So this data value, this Trader Joe's yogurt, is increasing the line, meaning it has increased the y-intercept. It's not really doing much for the slope, though. Okay, it's just kind of pulling because it's in the middle of the line here. So it's not really changing the slope much, but it is increasing the y-intercept. The correlation, that data value is making the correlation weaker because it's outside of the rest of the data. So that data value is making the correlation weaker, and it's pulling the line up, meaning the y-intercept would be increased because of that dot, but the slope isn't really affected. So slope not affected, y-intercept increases because of that dot, correlation gets weaker.